Hello everyone, welcome back. So let's try on a problem actually calculating our inlet performance and use those skills we've gained so far. So we have an aircraft, it's flying at an altitude where the ambient static pressure is 10 kilopascals, there we go. And the flight Mach number is 0.85. The total pressure at the engine face is measured to be 15.88 kilopascals. We're going to assume that the inlet is adiabatic, nice, and that we're just a regular air with a ratio specific heats of 1.4. We want to find out what the inlet total pressure recovery is, the inlet adiabatic efficiency, and the non-dimensional entropy. This is a cool one. We'll get to that one last. So let's go for it. Now, if we're going to find the inlet total pressure recovery, we have to figure out what our total pressure actually was before the inlet. Like what was beforehand, so we can tell how much we lost. So to do that, it's not too hard, because before we reach our inlet, before we hit anything, we can assume that that's an isentropic deceleration to zero. If we're going to pretend like it's slowed down, we can use our isentropic relations. And so the ratio of my total pressure to my static pressure outside is simply equal to this guy. I know my Mach number, I know my ratio specific heats. I can plug it in and I get that that's about 1.604. And I can then use that to calculate my total pressure before the inlet. Get really used to using the chain rule to solve for things. It will make it easier because we're going to have lots of ratios as you go through this course. So we have a ratio 1.604. I put in the wrong order. We have the 10 kilopascals. And so my total pressure before the inlet is 16.04. As we can see up here, afterwards it's 15.88. So we have lost some. So all you do is calculate that ratio. Our total pressure recovery is simply what is our total pressure after the inlet and what is our total pressure before the inlet. So it's about 0.99, which is honestly pretty good. Now let's calculate our adiabatic efficiency. So we had a nice equation for this. And it simply says, okay, yes, you lost some total pressure. Like, it's not a totally isentropic process. And so we have that same isentropic relation right here. Same isentropic relation. But we're adding in this adiabatic efficiency term right here to account for the fact that, we're not doing this perfect. You're like, but you said it's adiabatic right here. I totally did. But it's more saying, like, how efficient is it at turning my kinetic energy into enthalpy? And so, kinetic energy into an increase in pressure. It's not perfect at that, even if it's perfectly adiabatic. As a note, I realized that I forgot this exponent up here. That should have been right here. So, if you're wondering what happened there, I just forgot to leave it on. Those are the same equations. Now, this one right here, I need to rearrange it if I want to solve for the adiabatic efficiency. I can do that with a little bit of algebra. And this right here, we don't have that ratio. However, we have two ratios that are really similar to it. If we multiply them together, we get that second ratio. So if I solve, I get an adiabatic efficiency of 0.9775. So it's doing a pretty good job of transforming my kinetic energy into that increase in pressure. Where's the rest going? Well, it's increasing the temperature unnecessarily. That's the big thing here. Okay, and let's see right here. So this ratio, I want to go ahead and show you how we get that. So PT2 over P naught is the same thing as me taking this guy, PT2 over PT naught, and multiplying it by the inverse of this guy. So terrible handwriting, apologize. P naught over PT naught. So, nope. Almost looks at it. There you go. Not the inverse. There you go. So the PT naughts cancel, and I have what I'm looking for. So that's how we find that ratio. We just use the other two ratios we've already calculated. Okay, so that's two down. Get our total pressure recovery, our inlet adiabatic efficiency, and now let's get our entropy rise. So our entropy rise is simply a function of our drop in total pressure. Or I should say our drop in total pressure is a function of our entropy rise. So we've seen this equation in the past. We kind of rearrange it sometimes to calculate the total pressure ratio, other times to calculate the entropy. And so if I know my total pressure recovery, I can say, well, that difference, that reason that this is 0.99 is because I am actually increasing the entropy of my air. And when I do that, I'm reducing my useful work potential of that air. So using this value, we plug it in, we rearrange a little bit, and we get our non-dimensional entropy rise. As a note, we call it non-dimensional because entropy and your specific gas constant have the same units. So when I divide them, it's just a number. It comes out to be 0.01. So that is it for this problem. Thank you all so much for listening. Hopefully this helps you see how you can use these equations and begin plugging them in. And I'll see you all next time as we keep on moving through our turbojet engine. Have a good one. Bye-bye.